Welcome to the GridWise Architecture Council's video library. The following presentation by Alaa Mahjoub, entitled Building the Digital Grid Architecture, Integration of Digital Technologies, was presented to the GridWise Architecture Council on January 21st, 2026. Welcome, Alaa.
It is a real pleasure and honor to talk to you today. I'm an independent digital business advisor, and I'm going to talk to you today about building the digital grid architecture, integration of digital technologies across cloud, on-premises, and the edge for intelligent operations. Our agenda today includes the key concepts and the definitions. Then we are going to go through the digital technology domains, the reference architecture, and the key deployment models. And then we are going to go through the key integration patterns, scenarios, and the reference architectures. In this presentation, we envision the digital grid as a cyber-physical system of systems, which is an engineered system that orchestrates sensing, computation, control, networking, and analytics to interact with physical assets and the humans across the grid's functional domains, as well as other digitally enabled ecosystems. The digital grid can manage rising volumes of renewable energy while enabling safe, real-time, secure, reliable, resilient, and adaptable performance, as well as cross-sectoral value creation. The digital grid as a cyber-physical system consists of two components, the cyber components and the physical components. And in this presentation, we are going to call the cyber components as the digital technology domains. So, what are the digital technology domains? And what is the relationship between the digital grid functional domains, digital technology domains, and the digital technology deployment models? In fact, the digital grid includes 7 functional domains, namely customers, markets, service providers, operations, generation, transmission, and distribution. And these functional domains actually are utilizing 8 digital technology domains: information technology, operational technology and the Internet of Things, engineering technology, consumer technology, artificial intelligence and data and analytics, cyber physical system security, telecommunication, as well as system integration tools. And these digital technology domains can be deployed using 4 key deployment models: the edge, including the industrial and the consumer edge, the on-premises deployment model, the cloud deployment model, as well as the hybrid deployment model. And meanwhile, the digital grid can also connect to digitally enabled ecosystems from other sectors, such as the transportation sector, oil and gas, water, buildings, and so on and so forth. So, what is the digital grid intelligent operations then? Digital grid intelligent operations is an operating model which digital and artificial intelligence technology enable utilities to create value across customers, assets, and markets through predictive, self-optimizing, as well as autonomous operations. It involves delegating decisions to assets through decision intelligence and market-driven price signals. And intelligent operations is enabled by software-defined assets as well as digital twins, which together create intelligent industrial assets that can dynamically respond to changes in the external environments. And achieving intelligent operations requires holistic integration of engineering technology, consumers technology, information technology, operational technology, telecommunications, artificial intelligence, data and analytics, Internet of Things, and cyber physical security. And this operating model actually enables optimized asset utilization, customer engagement, market participation, as well as adaptive cyber physical security of the grid. What is the reference architecture of the digital technology domains? In fact, the design and the implementation of the digital technology domains can be guided by the GRID's Digital Business Technology Platform Reference Architecture. The GRID's Digital Business Technology Platform Reference Architecture is a modular architecture that includes 5 modules: the information system platform that runs the organization's IT applications, the customer experience platform that engages with organizations' customers, the Internet of Things platform that senses and controls the organization's physical assets and things, the ecosystem platform that manages the organization's ecosystems, in addition to the data and the analytics platform that manages and analyzes the contextual information of the organization. It is worth noting that the digital business technology platform is an integrated fabric that includes overlapped capabilities rather than a set of isolated architectural building blocks. What are the key deployment models? This is an example of key deployment models of the digital grid technology domains across cloud, on-premises, and the edge zone. So here we have the edge zone and the on-premises zone, as well as the cloud zone, where a customer experience platform and the ecosystem platform are typically deployed on cloud, while the data and analytics platform is deployed across cloud and on-premises zone. And meanwhile, the information system platform here is deployed across cloud, on-premises, and the edge. Meanwhile, you have here the industrial Internet of Things platform is deployed across the cloud and the edge. And at the same time, we have here a lot of operational technology and industrial Internet of Things systems and architectural building blocks that are deployed across the on-premises and the edge zones. It is worth noting that all these platforms, systems, and architectural building blocks are connected to each other through what is called integrated network infrastructure and converged communication services. In short, the various deployment models, on-premise, cloud, edge, and hybrid, can be used for deploying of the 5 sub-platforms of the GRID's digital business technology platform. Let us now go through key integration patterns, scenarios, and reference architectures. We are going to start with mesh application and service architecture integration. The mesh application and service architecture integration pattern is commonly used to implement the digital business technology platform. So here we have the digital business technology platform reference architecture that leverages the mesh application and service architecture integration pattern, which in turn includes 3 architectural patterns: the multi-experience applications pattern and the microservices pattern, as well as the event-centric pattern. And how it works: here we have the customer experience platform that leverages the multi-experience application pattern and to connect the customers to the platform through things such as web, mobile, conferencing, social, chatbot, as well as a smart machine. And meanwhile, the Internet of Things platform is using the same architectural pattern to connect the physical assets and the things. And at the same time, the ecosystem platform is leveraging the inbound and outbound APIs as well as API mediation to interconnect the ecosystem organizations to the platform, and all the sub-platforms are also leveraging the microservices and event-centric integration pattern. Let us now have a closer look at the event-centric integration. The modern event-centric integration pattern is gradually replacing the traditional point-to-point based integration patterns. So here at the left-hand side, we have traditional point-to-point integration, and at the right-hand side, we have modern event-centric based integration, where the decoupling between the event producers and event consumers enables adding producers and consumers without impacting the rest of the system. This is an example of applying the event-centric integration pattern at the industrial edge. So here we have at the industrial edge an operational technology system that uses an operational technology protocol such as the Modbus RTU or Modbus TCP. Meanwhile, we have also an operational technology gateway that translates this protocol into a message queue telemetry transport format and publish it to the message queue telemetry transport server in the form of unified namespace topic, where systems such as Industrial Data Hub, Data Historian, SCADA, Manufacturing Execution System, and other industrial applications can subscribe to the published topics. Let us now go through some illustrative cross-domain integration scenarios. Here, this is the digital grid cross-domain integration landscape, where we have here at the industrial edge an OT network and an IT network, and also at the on-premises zone, we have an on-premises OT network and on-premises IT network. And here we have the cloud zone, which with its own network infrastructure. All these networks are connected to each other through the wide area network part of the integrated network infrastructure and the converged communication services. And in this diagram, it is worth noting that the OT traffic is shown in red color, while the IT traffic is shown in green color. So the first integration scenario is spanning the industrial edge and on-premises zones, and it is about edge to on-premises integration of a mission-critical operational technology system that uses command response exchange. And using command response exchange means that the system should ensure that the command is correctly executed at the field. So here we have a mission-critical operational technology system which is connected to the OT network and using an OT protocol such as IEC 60870-5-104. And meanwhile, you have at the on-premises zone a national or regional control center that includes a SCADA system, which is connected to its OT network as well and using the same protocol. And here is how the control and real-time monitoring data are exchanged between the SCADA system and the field equipment. The second integration scenario is spanning the industrial edge on-premises and the cloud as well, and it is about leveraging data ops to integrate operational technology and information technology data with cloud analytics via industrial data hub pipelines. So we have here at the edge zone an industrial data hub which acquires the data directly or indirectly, either through the operational technology system or indirectly through the message queue telemetry transport broker, and it ingests the real-time data into two destinations. The first destination is in the on-premises zone, which is the asset performance management system, which is installed there as part of the information system platform. And the second destination is the cloud-based data and analytics platform. What about the non-real-time data? The non-real-time data is acquired by the on-premises data gateway of the data and analytics platform, and also ingested into the data and analytics platform at the cloud, where it is combined with the real-time data and analyzed together to provide insights to the corporation as well as the relevant ecosystem organizations. The third integration scenario, it is spans the industrial edge and the cloud, and it is about integration of operational technology data with cloud applications, digital twins, and machine learning models by industrial Internet of Things platform. So at the industrial edge here, we have an industrial Internet of Things gateway, which acquires the data either directly from operational technology or industrial Internet of Things system, or indirectly through the message queue telemetry transport broker. And the destination of this data is the cloud-based industrial Internet of Things platform. And here, how the data is actually flowing between the OT and the message queue telemetry transport broker all the way through the industrial Internet of Things gateway until it reaches the industrial Internet of Things platform, and combined with the data coming from the data industrial data hub, and finally consumed by the digital twin and the machine language model, as well as other cloud application, enabling the utility to realize its software-defined assets and intelligent industrial assets to achieve intelligent operations. The fourth scenario, it is also spanning industrial edge, on-premises, and the cloud zones, and it is about asset-centric grid security that leverages a cyber physical system protection platform. So at the cloud zone here, we have a cloud-based cyber physical system protection platform that performs operational technology, asset discovery, visibility, and categorization, in addition to detecting and fixing some security or the security issues. And it also can integrate with other cybersecurity solutions. How the data is acquired, we have here two cyber physical system protection platform data collectors. One is located at the industrial edge, and the other one is located at the on-premises zone, and they perform a passive and active monitoring of the operational technology assets, and they forward the asset information to the cloud-based cyber physical system protection platform. In this architecture, we have here also an operational technology security appliance that controls the communication between the edge operational technology network and the IT network, and it includes capabilities such as firewalls, intrusion detection and intrusion prevention sensors, access control list, and the VPN. And here also we have the edge security appliance that controls the communication between the edge IT network and the wide area network. Regarding the message broker here, the message queue telemetry transport broker, all the message queue telemetry transport headers and payloads are encrypted using transport layer security. And regarding the industrial edge active components in general, all the appliances, including firewalls, gateways, cyber physical system protection, data platform, data collector, are authenticated via X.509 certificates. And here, how the data flows from the data collectors to the cyber physical system protection platform. The last integration scenario, it spans the cloud zone, on-premises zone, but now we have the consumer edge instead of the industrial edge. And it is about integration of consumer edge technologies So we have here the consumer edge, and it includes the 3 LANs: an edge utility management energy VLAN, an edge utility management IT VLAN, as well as an end user consumer IT VLAN actually. So in this OT VLAN, we have things such as smart meters, battery management systems, utility managed electrical vehicle chargers, HVAC appliances, as well as photovoltaic inverters. And in this IT VLAN, we have things such as edge analytics appliance, which can also detect and report anomalies at the consumer edge. And at the end user side, we have here at the consumer IT LAN things such as energy management system, user interface, mobile apps, as well as home dashboards. What about okay, how the data is acquired? First, it is acquired using the utility management consumer edge gateway that includes energy management system built-in core applications, energy management system API, protocol translation, security, and policy control capabilities. What about the destinations? You have here 2 destinations. The first destination is located at the on-premises zone and connected to the on-premises advanced metering infrastructure network, and it includes metering data management head-end system and metering data management system. And at the cloud zone, we have a data and analytics platform, which is cloud-based, of course. So the meter actually sends the data to the neighborhood concentrator using radio frequency mesh, and the concentrator receives the data in the form of a metering protocol such as IEC 62056, and it relays the data through a 5G private access point name all the way through the telecom operator multi-protocol level switching network until it reaches the utility virtual private network gateway and ingested into the metering head-end system, and it is terminated there. Here also we have the real-time data acquired from all these devices is actually acquired using an OT protocol and the same metering protocol by the gateway, and it is translated to message queue telemetry transport format, and it is ingested to the cloud into the data and analytics platform. And we have here an alternative path for the metering fallback, where the meter can use it in case it loses the connection with the RF mesh network to the concentrator. And having done this, we have now the data is in the cloud, at the cloud zone, at the data and analytics platform, where it can be actually enabling the utility to provide services such as energy as a service, electrical vehicles, charging as a service, virtual power plant as a service, storage as a service, grid and market participation, as well as automated bidding and demand response. What about the end user? How can he monitor and configure his devices? He can do that through connection, through Wi-Fi, LAN, SSID, and HTTPS protocol and REST API to the gateway, or he can do this actually through connecting to the cloud. He can also monitor and configure his devices from connection to the cloud. Let us now go to the communication integration. This is a contextual level architecture of a traditional fragmented enterprise networking and communication, where we have 3 types of separate networks: IT system networks, voice and video networks, and OT system networks. They are not connected and they are separate. And this is a contextual level diagram or architecture of a modern integrated network infrastructure and converged communication services, where all these types of networks are combined together to form the integrated network infrastructure and converged communication services, which has as well a unified network management capability. And having done this, and we now enable the information collaboration, unified communication, OT, and IIoT systems, hardware and applications to speak to each other and communicate to each other. And having done this, the human layers, including the users of the 7 functional digital grid domains, can now access their information systems and unified communication systems through their IT workstations and unified communication optimized phones and the devices. In addition to that, the operational technology users in the functional domains can also access their operational technology workstations, control center console, as well as displays such as large screen displays, for instance. This is a conceptual level reference architecture of the integrated network infrastructure and converged communication services. And we are not going to go through each architectural building block of this diagram, but the message from this slide is that this diagram actually maps the 7 layers of the ISO Open System Interconnection Protocol into actual hardware and software components. And this was the last slide of my presentation. And actually, the slide deck includes supplementary architectural material. And I will leave the full deck with Jimmy and Susan for your reference. Over to you.
Thanks, Alaa, for that insightful presentation. For more information about the GridWise Architecture Council, please see our website at gridwiseac.org, and don't forget to subscribe to our YouTube channel at the site listed. Thank you.